So in this segment, we're going to validate Gauss's law in two ways. We're going to do it analytically, and we're also going to do it numerically or computationally using something called finite elements analysis. So let me start by writing out Gauss's law. So I'm going to put the subscript for S. And then on the right-hand side, we have Q enclosed divided by a fundamental constant. Now, you might have seen this written in different forms. Just to be clear, this is the integral form of Gauss's law. There's also a differential form, and we'll probably cover that later as well. So what this says is that if there's an electric field and we enclose some arbitrary point in space by a surface, and we integrate that electric field and the dot product of that electric field with that enclosing surface, then we're going to basically calculate the enclosed charge that's bound by that surface divided by the free space. I should say the permittivity of free space. So what we're going to do is set up a simple problem that we know we can get an analytical definition for. And we're going to apply the numerical technique to solve for just this left-hand side. And what we should show is that if we work through all the calculus for that simple setup, then we will end up with the same result that we see over here on the right-hand side. So let's get this set up for a simple setup, I guess, that we can go through. So I'm just going to pull this out and park it over here so we can keep track of the thing that we're trying to solve. And let's just get rid of this. Now, what I want to do is come up with the quantities that are all defined here. And there's really three things that we need. We need to be able to break the integral up. So this closed surface integral, what exactly is that? We need something that defines the E field. Right now, we just have a representation of something that of an E field that's going to be set up from some source, and we haven't really defined what that is yet. So an analytical function for what the E field is going to be needed, and we're going to need that analytical function for that segment of surface that's bounding, that's really tied to this closed surface integral. So the first thing I wanted to do was let's come up with a scenario that is going to be easy for us to solve. So let me change the stylus here. If we can use a point charge in free space, so I can say, here's just this made-up charge that I put in the middle of nowhere, and if I look at physics textbooks, you'll often find that this is one of the first things that you'll see in electrostatics is that we have a formula that connects the electric field that is basically produced from this point charge. And there's an analytical definition for this. So these fields are set up so that basically they're equal amplitude and direction in the appropriate coordinate system. So we'll talk about that coordinate system in a second. Let me just put the analytical formula for the electric field. Again, it's a vector, but this is the electric field that is produced from a point charge in free space. So it's the charge. We represent that as Q, typically in coulombs, and we'll say we have some constants. And again, all I'm doing is copying a formula. I'm not trying to derive this at all. This is something that you'll find in your textbooks. So Q divided by some constants here over the distance, the radius in this case, the distance in spherical coordinates, and the direction, not getting into unit vectors here, but that's exactly what that is. It tells us that it tells us the direction, because we know that electric field is not just the amplitude, but it's also pointing in a direction. And in the spherical coordinate system, we're basically saying that any point in space can be defined in terms of its radius, of that distance vector in spherical, which is represented by r from that q, from that charge. So that's the direction. So it would be appropriate to have a little bit of a setup of what that means in context of our problem. We want to put an enclosing sphere, and imagine if I was able to just, let's say, in a spherical system, one of the easiest objects that we can think of, if we want to enclose that charge, and again, this is an imaginary surface about a charge that we want to integrate over. So that's the closed integration. So we're about to define these components for the element of area, but if we can just settle on, let's go ahead and grab any arbitrary size sphere, and we're going to make it a fixed value, and we're going to call that capital letter R. Okay, so that's a constant, whereas the value, the other value that we'll define in the spherical coordinate system is the variable r. So these are ultimately going to be related. So if we choose to set a sphere of a constant radius r, we're going to end up replacing this value that's a variable r with a constant, and it's still going to be pointing in the direction of our coordinate system setup. So let's talk about that now. So I'm going to start by drawing out our Cartesian system. And I'll do my best to draw this as if it's in 3 dimensions. Try to put the appropriate perspective on here. So if I start with Cartesian coordinates, I can define those as x, y, and z axes. So following the right-hand rule, I know that I need my x vector, or I should say my unit vector. So here's the x-axis, and I know that because it's pointed in the x direction. And a unit vector is represented with the hat, as we've already seen up in our electric field representation. So I have the y-hat direction, and then I have the z-hat direction. And again, this is right-hand rule, meaning that if you cross the x into the y, it's actually going to become another unit vector that points in the z direction, and that continues on with the y into z, and then z into x. So this is a perfectly defined orthogonal coordinate system. So what we're going to do now is define another orthogonal coordinate system that's going to be the spherical system that's based off of this Cartesian. So what I'm going to do is, let's say that this is going to be the point, the origin, and by the way, there's it's no coincidence that this is really aligned with our problem, where you can imagine we're going to be placing our charge, that Q plus that we have on the left-hand side up here, is going to be placed at the origin, so we can define that electric field as a function in terms of r instead of x, y, and z. So let's say that location r, we're going to use the variable r, not capital R yet. This is a vector. So this is r variable with a vector sign. And what I want to do now is come up with a way to define, let's say, the element. I want to get to that surface element that we have over here on the right-hand side. So if I can think of defining this in 3, with x, y, and z, with the Cartesian, we basically had these 3 orthogonal components of x, y, and z. For spherical, we're going to look at these 3 orthogonal components that are going to be r, theta, and phi. So we've just defined r, but I haven't given you enough information to get to a point in space relative to the XYZ coordinate system, because we haven't defined this theta and this phi yet. So we're going to do that now. So r is the distance from the origin, and then theta is going to be defined as the angle of r from the z axis. So that angle If theta was 0 in the example that you see right here, r would appear to be pointing directly up along the z-axis. Now, if theta was 90 degrees in this case, r would extend down, and it would appear to be directly in the direction of the y-axis. And there's a little bit of an ambiguity because we haven't really defined where on the y-plane, and that's where the projection comes in. So what I can do now is use the trig that I know. What I want to come up with is what's the component that's in the xy plane. So imagine if we shined a light coming directly down the z-axis, and let's say this was maybe we were using a stick or some ruler that was going to define that direction. Well, that shadow would ultimately be cast on the surface. And let's say that's a table in the xy plane. So this is also a vector, but it's not r, it's a component of r. And if we use trig, we can say we know that the right triangle, let's say that's getting formed. Let me use a different color here. If I had a segment here in space, this forms a right triangle. And now I know that if I use trigonometry, I can calculate either this component or this component. And it's no coincidence, again, that this component here is directly related to that shadow. So that is our projection. So trigonometry tells us that if I know this r vector here, that's the hypotenuse, this would be the opposite. So I'm going for the opposite angle, and I know that sine of theta equals this component. Well, let's just go ahead and say the opposite. I'll just say opposite OPP over r. So if I was to rewrite this and solve it just using algebra, all I have to do is multiply both sides by r, and it's going to give me r sine theta equals this opposite. And that is our projection. So we just solved for what this value is going to be. So now I'm going to write this as, I'll put it up here, I'll say r sine theta. So that's my projection. And that's important because now that I have my projection in the xy plane, then that's where my final value of phi comes in. Phi is the second angle, which is defined from the x-axis to the angle that projection resides. And that's it. I have all the components that I need. So now, one thing to keep in mind is that just like we have unit vectors for the x, y, and z Cartesian, there's also unit vectors here. And I've got an r hat that is always pointed away in the r direction. So I'm going to give that a little hat symbol. And then I've got a theta that is going to be pointed in the direction of that theta as if I moved it, towards the z and then away from the z. Well, this theta hat gives me a orthogonal direction as well. And then I also have, it's getting a little bit hard for me to represent, but imagine that this projection, I could say, this projection, the angle phi here as it swings through is going in this direction. And if I was to try to put that in space, it might look something like this. Phi would be going in that direction. So I have unit vectors for these. So I've completely, mapped my spherical representation I've completely mapped my Cartesian representation into my spherical representation. And all of this was to say, what I'm after is that element of surface area. What I'm trying to get is this component here. And one way to get there is to have this defined. And now this is a reference that you'll find in many calculus books. If I want to represent an element of volume, that element of volume is going to be represented as r squared dr sine theta d theta d phi. Now, that's a volume. If we have a constant radius, then this turns into an area element. So I can also say that dA in this case is going to be represented by a constant r squared. There's no longer a differential for dr, but I still have my sine theta d theta and my d phi. So let's do some bookkeeping here. I'll get rid of this. And let's go ahead and hold on to our coordinate reference here, because this might come in handy. I'm not quite sure yet, so we'll just hold on to it just in case. So we'll bring that over here. Maybe I can resize it. I lost a little bit of resolution, but it should do the job. And then let me bring this and get a little bit more organized here. So if I look at this differential area defined by this term, the only thing that's missing to make it match this symbol is the vector. And one way to think about that is we can always define areas or segments of areas by their normal. And in this case, we're taking a subset of this sphere. So to make this a vector, imagine that I went out from the origin where the charge is located, some distance r, capital R, and I want to capture a small segment of area. Well, if I use this coordinate system and the combination of r, theta, and phi, I can basically sweep out this tiny segment of differential area that's at a distance, capital R, which is where that sphere is, and I can also include the fact that it does have a direction, and this direction is nothing different than the unit vector r hat. So this r hat that I have represented here is literally just following out in that same direction. You know, I can map this coordinate system on our example and it really makes no difference. It's the same thing. This r vector is equivalent to the magnitude of the variable r plus this r hat. I shouldn't say plus, I should say times. And that's the unit vector. So, and here it is represented here. So now with that definition, I can tack on the r hat here that represents the direction of this element of surface area. And that's what I'll do. So now all I have to do is put the vector sign on that. And I've completely mapped this component of dA with this thing that we talked about, this figure that we've talked about using our representative sphere that we want to integrate over in spherical coordinate systems. And then I've got the next entity is my electric field. So I can take that electric field and, well, we've already talked about that, right? This is the quantity that we've pulled out of a textbook. And I've got my two elements. So these are defined as vectors, and I can see that they actually have their amplitude and direction, so they are true vectors. And I know that we can do a dot product of two vectors, so that's good. So the remaining thing to do is understand and decompose out the integral over the entire surface, and that corresponds to this segment of differential area, which we've drawn out right here. And we'll do that next. So what we've just said is if the thing in the red box here that we're calling dA is equivalent to this thing in Gauss's law that is part of our integration. We also have a graphical representation of what that dA is. So this little patch we call the differential element. So we may as well call that dA. I'm going to try to get a little bit more consistent with my coloring, so I'll make this red font represent the thing that I have encapsulated in the red box here. So this little patch element is what we're calling dA. And the same with the E field. We have the electric field that we've already defined. Well, I can say that this arrow, these are the vector field graphical representations that are pointing out in a space. This is the vector E. And that's what it looks like at that particular point in space, at that little patch. And that's also a vector hat. So I have E. I have E with the vector that's represented graphically as the arrow coming from the point charge, and it follows this function in that direction of r hat. And then we have the surface segment, the differential area element, dA, that is defined graphically here, and that's also represented as these components. So what we want to do now is integrate this differential. So if we take that differential element of the surface area, dA, and integrate it around the entire sphere, then that's how we achieve the full surface of the enclosing volume. So the task now is really to break up this component here, which is the surface integral, and maybe we could define the bounds of that. And this is a good reference is our spherical coordinate system. So again, differential element here. We want to think of it in terms of sweeping that differential element so it goes full 360 degrees around in one direction and then sweeps the other direction as well. And those are going to be corresponding to conventions and definitions that we've used based on this spherical coordinate system. So what we get is instead of this enclosed surface integral sign, we're going to decompose this as two integral parts. So the first one is going to be integrated from, let's say, phi equals 0 to 2 pi. And that's by convention. So if you look at the graphical representation of what that would be, is imagine we're sweeping phi from 0 degrees, which means this r sine theta would be pointed directly along the x-axis. And imagine sweeping that projection in the plane all the way 360 degrees around, so that phi ends up right back where it started. That's what that integral segment means. The other segment that we want to include is sweeping it around theta. And the convention that we use there is going to be, do the integral sign again, and this is going to be theta now is equal to 0, and we're going to sweep that to pi. So if theta is 0, our r vector is directly in line with the z-axis, and if theta equals pi, that's the same as 180 degrees. It would be pointing in the negative direction. So by accomplishing these two integrals, we essentially are making this patch, sweeping it in both directions, stretching that patch out, so that ultimately we end up with the entire sphere. That's really all that's taking place right now. So we've successfully decomposed this symbol for the integrand that's represented here in green, as well as the components E and A. And that's the next thing, is that we'll fill that in, and then we'll see if we can simplify and then get the integration going. So let's just start copying these components. So we need an E, we need the dA, and the dot product of the two. So let's just bring down the components that we see defined by the electric field. So I'll go ahead and try to keep the coloring. Okay, so there's a Q, there's the r hat vector, unit vector divided by 4 pi epsilon naught. And here's our r squared. So remember, that's the function of that defines the electric field from the point charge. And we'll go ahead and put that in parentheses so we can just keep track of everything. And we'll remember that there's a dot product here. And now I'll fill in the differential area component, which is going to be this. So if I put brackets around that, I'm going to say R, capital R in this case, squared times sine theta d theta d phi. And I can't forget that there's a r hat vector there as well, so that also has a direction. So now, well, we start evaluating. Probably the first thing that we would want to do would be pull out anything that might be a constant. So we'll avoid any deep discussions about the rules of integration, but one thing that a lot of us probably remember or know is that whenever we integrate a function that has constants involved, those constants can actually come out of the integrand. So we can start to look at some of these things that are constants. One thing that we notice also is that we have a small r in this example, and we have a big R in this example. We decided early on to define our differential area element at a fixed radius. Well, this is the same area that we need to evaluate the field over. So it probably would have made a little bit more sense for me early on to equate this R is equal to the capital R. Okay, so small r squared in this function is equal to capital R squared, our fixed distance of whatever our radius is. And that's by definition. We are going to integrate over that sphere, and the field value at that point would basically be at the radius of the sphere. So it turns out that's actually a constant. So with that, we can go and identify some additional constants. I'll just try to circle some of the things that we know are constants. Here, Q, that would be a fixed charge. In this case, we're just showing one small charge there. So Q would be a constant. 4 pi epsilon naught would be a constant. Actually, so is r squared, now that we just made that distinction. These are all constants, so these should be able to come out. We've already talked about r squared, that can come out. Now these are not constants. I guess I should say these pertain to our integration, right? So we have the bounds that are defined by the integrals, and these are the values that we're integrating over, and certainly the r hat is going to show up in that dot product. So we're going to make a little space and expand this out. We can probably just get rid of this for now. And I'm going to hold on to this, but slide it over and shrink it just so you can check my work, I guess, as we go and make sure that I'm not losing anything. But this is ultimately the quantity that we're going for here. So let's just say this equals, whoops. So let's just say this is going to be equal to me rewriting it in this form, and I'm going to give myself a little bit more space here. So we want to bring out all the constants first. So I'll draw the integral signs in a second. Let's bring out Q. Let's bring out the r squared on the numerator. We're going to leave the vector sign in since that pertains to the dot product of those functions. So I only have on the numerator, I have Q and r squared that's come out. I could even I guess scratch these out as I go just to keep track. On the denominator, I have 4 pi epsilon naught. And I also have r squared. And of course, in this case, we can also recognize that, well, these two should cancel out. R squared over r squared is going to equal 1. So now we're gonna go ahead and bring the integral down, or I guess I should say copy out the integral. So it was just phi 0 to 2 pi, and of course it's a double integral. Theta equals 0 to pi. Now let's keep track of the things that we had in brackets before. Switch colors just to try to stay consistent here. We brought a lot of things out. The only thing remaining now for the electric field, since everything else that we found was ultimately constant, the only thing left for the electric field is this r hat. So we know that there's a dot product coming up. So copy over the parts now for the element of surface area, which is also a vector. So what's remaining here? We have sine theta, d phi, r hat. Sine theta, d theta, d phi, here's an r hat. Now this might at first glance look a little intimidating to take the dot product of this, until we recognize that, well, the dot product of any two vectors is nothing more than the multiplication of the respective components and then added up with all the other components. Well, the electric field, we pulled out all of the constants. It turns out it was a simple enough problem where the only thing that we're left with is just the direction itself. So that's basically a constant of 1. So we have an r hat vector that represents the E field. So there's only the r hat component here, and it's multiplied by 1. In the right-hand side with that differential surface element, there's also, you might see the variables for theta in phi represented in here, but the component is still the r hat component. It's the exact r hat component as we have defined up here in our problem setup with the charge at the origin, and we use spherical coordinate systems to define the electric field as well as that segment of surface area around this sphere at a constant r. So it turns out this ends up being really nothing more than these two unit vectors that are dotted with each other, because this doesn't impact that dot product. It's the components. So just like maybe we've learned that x hat as a unit vector dotted with itself is 1, well, the same thing is taking place here. R hat dotted with itself is 1, which means that this whole segment here can be rewritten. We can remove that dot product, meaning we take the dot product, and we simply end up with sine theta, d phi. There is no more vector. There's no more direction anymore, as you would expect with the dot product. The rules of the dot product are that the result is going to give us a scalar, and that's what this is telling us so far, is that we're going to end up with a scalar. So next, what we want to do is redistribute, I guess. I shouldn't say redistribute, but I should say let's organize this this integrand so that we can do the separate integrals for our two-part integration here, and we'll do that next. All right. So just to keep track of things, we're going to go ahead and move this segment over here. Of course, we don't need this. To give us a larger space here. Actually, let me shrink this as well. Hopefully the resolution doesn't go down too much. I think that's probably fine for us to map everything over. So let's go ahead and get this set up to do the integral now. So what I want to do is let's write. I'll see if I can fit this in the remaining space here. So I'll say this equals, and I'll just go ahead and rewrite my constants here. What did I have? A q over pi. I think I missed a 4, so it's off the edge of my screen. So if I put the 4 pi epsilon naught, that looks good. And then if I draw my first integral, what I can do, let me give a little bit of space and explain this. I'm going to put theta, actually, let's try to keep consistent here. If I put phi equals 0, and again, I'm going to 2 pi, and I'm going to give myself a lot of space here. This would be theta equals 0. And remember, I'm going to pi. Okay, so bringing in the appropriate components, what I have left, I know it's hard to read now, but the only component of phi in here, this function doesn't have any phi components. It only has the d phi. So literally, I can just integrate over d phi. And that's about as simple of an integrand as we can get, regardless of the coordinate system that we're in, right? So we should all remember how to do this integral. It's a definite integral as we integrate d phi, going from phi equals 0 to 2 pi. This is multiplying. So the two-part integral that we've been doing here is perfectly fine to bring out the components of the respective integrals. So I can integrate this portion with respect to phi, and I can multiply that by the portions that are relevant for theta. So the only thing left in this function was sine theta d theta. Okay, so this is a little bit more complex than this integral because I have to integrate, it's not just d theta, but it's actually sine theta d theta. And there's an integration rule for that. So I've got my constants, I've got my integral over phi, and I'm going to multiply that result to the integral, the definite integral over sine theta. So now let's do this integration. Let me clean up one thing. I feel like this, try it again. This runs the risk of giving the impression that we're doing, like we're missing an addition or a subtraction. So if I bring it closer together, maybe that's a little bit more, telling that this is going to be this double integral. We just multiply these components together. So we multiply the constant by this portion by that portion. So let's whoops, gotta change my tool. So I'm gonna just reproduce all this. So my constants, again, 4 pi epsilon naught. Now, let's integrate d phi from 0 to 2 pi. The notation that I'm going to use is I'm going to put the large bracket in. If I look up on integration rules and tables that you'll find in the cover of calculus textbooks, I'll try to leave a reference at the end. If you just integrate d phi, we know that the answer is phi. And the definite integral means that we subtract the starting point from the ending point. So if the integral of d phi is phi, I'm going to go ahead and put it here. So that's my result. I'm going to use this end of the bracket and use this notation. So I put the 2 pi and the 0 over there. And we'll talk about that in a second. If you're not familiar with that notation, there might be other ways to do this as well, but this is also a fairly common way to do it. So I'm about to integrate the second part, so I'm going to go ahead and set up my bracket for that. Now the integral of the second part here is just the theta portion of the integral. So integral of sine theta d theta, again, if we refer to integration rules, I know that the integral of sine is going to be negative cosine. So I have to really keep track of all my sign conventions, or I should say just my signs, negative or positive, as well as trigonometric. So I'll say negative cosine theta, and then my range here is going to be I'm going to be subtracting negative cosine theta of 0 from negative cosine theta of pi. So those are just the limits. So if you just see the mapping, I I keep the starting point on the bottom, the end point on the top, and this just implies my definite integral. Okay, so now let's I'll go ahead and fill out the bottom part here. So we'll bring this over, and I'll have q over 4 pi epsilon naught, and in my bracket, the definite, if I apply the definite rule to phi, it's going to be 2 pi minus 0. So 2 pi minus 0. And again, that's just the result of this definite integral from here to here. So we subtract the lower limit from the upper limit, and that's what we get. So now I have a negative. What I can do now, instead of having the negative sign, I'm going to bring that negative sign out. It's just a constant. It's a negative 1. So why not go ahead and bring the negative 1 out here? So negative 1 times here. And now I don't have to say negative cosine minus negative cosine. Instead, it's just going to be cosine. So I'm going to say cosine, and this time I'm going to actually put cosine of pi minus cosine of 0. And you can test for yourself if you left the negative sign in there, it would get multiplied across. This is not 19, this is negative 1 times q. So now I'm going to reduce this. If I say negative q over 4 pi epsilon naught, what's 2 pi minus 0? Well, I'm going to keep it in the brackets just to keep things as clean as possible. We know that 2 pi minus 0 is just 2 pi. We'd have to refer back to some trigonometry, which we're not reviewing in any depth here, but you can even just check this with your calculator, to be honest. Cosine of pi is actually negative 1. So I'm going to put negative 1, and now in parentheses, I'm going to put the cosine of 0. And cosine of 0, we know, is actually 1. So all this is, I know now, is basically negative 1 minus 1 is just negative 2. So we know that that's negative 2. I've got a negative sign times a negative sign. That's going to be positive. And I have 2 pi times 2. That's going to be 4 pi. So let's go ahead and put 4 pi on top times q over 4 pi epsilon naught. And as you've already probably guessed, we can cross that out, and we end up with q over epsilon naught. So now let's do this integration. Let me clean up one thing. I feel like this, try it again, this runs the risk of giving the impression that we're doing, like we're missing an addition or a subtraction. So if I bring it closer together, maybe that's a little bit more telling that this is going to be this double integral. We just multiply these components together. So we multiply the constant by this portion by that portion. So let's whoops, gotta change my tool. So I'm gonna just reproduce all this. So my constants, again, 4 pi epsilon naught. Now let's integrate d phi from 0 to 2 pi. The notation that I'm going to use is I'm going to put the large bracket in. If I look up on integration rules and tables that you'll find in the cover of calculus textbooks, I'll try to leave a reference at the end. If you just integrate d phi, we know that the answer is phi. And the definite integral means that we subtract the starting point from the ending point. So if the integral of d phi is phi, I'm going to go ahead and put it here. So that's my result. I'm going to use this end of the bracket and use this notation. So I put the 2 pi and the 0 over there. And we'll talk about that in a second. If you're not familiar with that notation, there might be other ways to do this as well, but this is also a fairly common way to do it. So I'm about to integrate the second part. So I'm going to go ahead and set up my bracket for that. Now the integral of the second part here is just the theta portion of the integral. So integral of sine theta d theta, Again, if we refer to integration rules, I know that the integral of sine is going to be negative cosine. So I have to really keep track of all my sine conventions, or I should say just my sines, negative or positive, as well as trigonometric. So I'll say negative cosine theta, and then my range here is going to be I'm going to be subtracting negative cosine theta of 0 from negative cosine theta of pi. So those are just the limits. So if you just see the mapping, I keep the starting point on the bottom, the end point on the top, and this just implies my definite integral. Okay, so now let's I'll go ahead and fill out the bottom part here. So we'll bring this over, and I'll have q over 4 pi epsilon naught, and in my bracket, the definite, if I apply the definite rule to phi, it's going to be 2 pi minus 0. So 2 pi minus 0. And again, that's just the result of this definite integral from here to here. So we subtract the lower limit from the upper limit, and that's what we get. So now I have a negative. What I can do now, instead of having the negative sign, I'm going to bring that negative sign out. It's just a constant. It's a negative 1. So why not go ahead and bring the negative 1 out here? So negative 1 times here. And now I don't have to say negative cosine minus negative cosine. Instead, it's just going to be cosine. So I'm going to say cosine, and this time I'm going to actually put cosine of pi minus cosine of 0. And you can test for yourself if you left the negative sign in there, it would get multiplied across. This is not 19, this is negative 1 times q. So now I'm going to reduce this. If I say negative q over 4 pi epsilon naught, what's 2 pi minus 0? Well, I'm going to keep it in the brackets just to keep things as clean as possible. We know that 2 pi minus 0 is just 2 pi. Now, we have to evaluate cosine of an angle. So in this case, we'd have to refer back to some trigonometry, which we're not reviewing in any depth here, but you can even just check this with your calculator, to be honest. Cosine of pi is actually negative 1. So I'm going to put negative 1, and then cosine, remember it's the minus, the definite integral is the top value minus the bottom value. So there's my minus sign. And now in parentheses, I'm going to put the cosine of 0. And cosine of 0, we know, is actually 1. So all this is, I know now, is basically negative 1 minus 1 is just negative 2. So we know that that's negative 2. So I'm pretty close to being able to reduce this down. So I can just multiply all this probably in this final step here. So I've got a negative sign times a negative sign. That's going to be positive. And I have 2 pi times 2. That's going to be 4 pi. So let's go ahead and put 4 pi on top times q over 4 pi epsilon naught. And as you've already probably guessed, we can cross that out, and we end up with q over epsilon naught. So this should be encouraging, because that was certainly a good bit of effort to get to this solution that we set up in the beginning. If you remember, the value that we have been kind of holding on to up at the top here this is really where we started. And what we said was that we weren't going to worry about the right-hand side of that equation of Gauss's law. But if you remember, we wrote this out early on, and Gauss's law basically states that this thing on the left-hand side that we just solved is equal to the q enclosed divided by epsilon naught. Well, it looks like this is close, what we came up with, but it's not quite exactly the same thing because we ended up with Q over epsilon naught. But if you keep in mind, what we did was we ultimately solved for what the charge was that was completely enclosed by that sphere that we put together and integrated around of a distance, a radius r, if you remember. So ultimately, this sphere that we made up and integrated around is enclosing the charge. So whatever charge was at the center turns out is the Q enclosed. So even though they look different because the names are different, that's exactly what we solved. So we ended up solving for the Q enclosed over epsilon naught, which happens to be the same thing that we represented here. So it's a pretty significant result, and it shows that, at least for the simple example that we put together, we can say that we've verified or we've calculated by using Gauss's law the amount of charge that was completely enclosed by this arbitrary sphere, which is a very important rule because we get to apply it to much more complicated things that might not be able to be solved analytically. So what we'd like to do with the subsequent session of this is we just went through the process to analytically solve Gauss's law. We're now going to set up a similar type of problem and go through a computational solution or a numerical solution using something called the finite elements method. And we're going to set up the same problem, and we should be able to verify that we're able to get the same result, and we're able to do a lot more by using the computational techniques that are based off of this law that we just verified.